It is now my honor to introduce my dear friend, my co-founder, my chief operating officer, Stephen Diamond, my benevolent dictator for life for CVXPY project, Stephen Diamond, to talk about Moreau, the new convex optimization solver that we've been working on.
Well, thanks so much, Parth. Yeah, really glad that we could do this conference, and I appreciate all the work that went into it. As Parth said, we have started a company with a third co-founder, Shane, as well. All of us are graduates of Stephen Boyd's research group, so we all did our PhDs here. Not really overlapping, sort of staggered. And our company is called Optimal Intellect, and our first product is a new solver, Moreau, which we're very excited about, and we're going to start sharing on Monday. Moreau is bringing together a lot of different threads that each of us looked at over the course of our PhDs. One thread was GPU acceleration. For many years, Stephen has been trying to figure out how to, this being Stephen Boyd, how to really take advantage of the revolution that in architecture that GPUs have provided. And it's taken a surprisingly long time to really utilize them well for generic convex optimization problems. And there are many reasons for this, which I won't get into too much in this talk. But it's only very recently that we've been able to build a generic conic solver that is getting substantial acceleration on the GPU. And this is based on work Parth did in his PhD. And so we've implemented these ideas into Moreau, our new solver. And so with Moreau, we're going from a world of solvers that are primarily on the CPU, primarily focused on just solving one problem at a time, and then not really thinking about differentiability. I'll say more what I mean by differentiability in a second, but essentially differentiating through a problem so that I can have optimization inside a training pipeline. And when we developed Moreau, our design principles were that everything has to be on the GPU. This is a really professional implementation. It's thinking about batching from the start. This is very important for learning pipelines and many workloads in modern systems. And then really good implementation of the backward pass. So these were our key design principles. Moreau, concretely, it's a conic solver. It takes a quadratic objective, which is something some of the newer conic solvers do. And it's, as I said, everything is running on the GPU. We also have a parallel CPU implementation, which can be useful in some cases and certainly useful for testing. But you can, with the batching, you can solve hundreds of problems in parallel and get enormous speedups. And everything interfaces very nicely with PyTorch and JAX. And let me say a little bit more about what I mean by differentiability, because it's a little bit confusing. So the idea is that I'm solving this optimization problem. And what are my inputs to this problem? They're the problem data, P, Q, A, B here. Right? These are the inputs that are to this box. And then the outputs are the variables, in this case, let's say X and S, the primal, and then the slash variables, but you can also do dual variables. So these are the outputs. And so the idea is that we're going to view this as sort of like a function, right, that we can embed in a bigger system. And then we can differentiate backwards through it and see how, if we want some change in the variable that it's output, how should the problem data change? It's a little bit of it's a very interesting concept and something we developed originally in the CVXPY layers package, building on work from others. But it's only with this solver Moreau that I feel this is really actionable, that this really just works. And so that's something we're very, very excited about. Moreau has interfaces to CVXPY and CVXPY layers, which is the package I just mentioned for using a CVXPY problem as a layer in PyTorch or JAX. It supports sort of the standard cones, except for we don't support semi-definite programs right now, though we expect to, at least to some extent. There's a really interesting compiled solver API. So of course we have the standard, here's my problem, solve my problem API. But we put a lot of thought into this other use case, which aligns more with this CVXPY layers world, where I have my problem structure in advance. It's like a parameterized problem. And so I can do a ton of pre-computation. I can do a symbolic factorization. I can do whatever I can think of, so that when I start solving batches of problems, it's as fast as possible. So this is something that we've thought about a lot. It is quite interesting. It is a commercial solver, but it's free for academic use. We're going to start getting out academic licenses. If you're interested, regardless of whether you're in academia or in industry, go to this website, moreau.so. I'll have it again at the end. And there's a forum, or you can talk to me as well today. We're really excited to share this with people and hear about the problems that they have. Benchmarks. These are more qualitative. We'll certainly be posting for benchmarks later. But we're seeing substantial speedups over the best open source solvers. So in this case, this was a comparison on the H100 versus sort of a souped up version of Clarabelle that's more suitable for batches. And we're seeing speedups that go from 10x to, in some cases, even 100x. And again, these are qualitative numbers, but we're very excited by the performance of the solver. We're very excited to share it. We've actually gotten great support from NVIDIA. We've been talking with them a lot, gotten a lot of advice from them about how to use better improve performance. Now I'm going to talk about 3 applications where you can see how Moreau is unlocking, making situations, applications of optimization that are previously very difficult research problems into just a simple, a few lines of code. One application is learning through model predictive control. Briefly, model predictive control is a planning framework where you're starting from some given state, X naught, and you want to choose an action or control input, U naught. I have dynamics that I know, which for it to be convex, it has to be linear. If it's nonlinear, you can handle that in various ways. I won't get into that. And the general idea is that I plan ahead some number of time steps, but then I only execute the first step of the plan, and then I replan. So it's closed loop, but it's looking ahead in a useful way. So it's not making myopic decisions. And the general idea is that I have convex costs, F and G, applied to my state and my actions. I have the dynamics, and then I have different constraints on my states and my actions. And combining learning with MPC is a really interesting approach where the costs, which are always a little bit always a little more, sometimes more art than science in choosing the costs. In this case, you can just learn the costs. But you are able to embed the things that like whether it's the dynamics, which come from physics, or constraints that are encoding important safety considerations about how something is physically moving. And as I mentioned, because this integrates so well with learning frameworks, you can imagine having pipelines that go from perception into MPC-based control, or many possible ways of setting this up. One interesting research paper that used this idea was by Angel Romero and others about agile quadrotor flight, sort of quadrotor racing. And they used MPC with learned costs in an RL setting. And they were able to be competitive with a model-free RL baseline and achieve better generalization, better robustness, better sample efficiency, better interpretability by having this useful knowledge that they had about the quadrotor system embedded in the learning pipeline. Another very interesting application, so this was a research paper. This took quite some time for the authors, and ultimately, and the training was fairly slow. But we believe using Moreau and the enhancements that we're going to bring there, this is just a simple application. It's very straightforward, just like you would solve a CVXPY problem. Another application is optimal power flow. This is the idea that I'm going to solve an optimization problem to choose how generators produce power to meet demand across a network. And this is really integral to how modern power grids work. The idea is that I have my variable P, which is the power production, and I have different costs at different generators. This is just linear. It can be more complex than this. This is a very simple version of the problem. And then I've somehow encoding my network physics. In this case, in linear, I have a linear model. These matrices A and F encode physics. And so I'm saying the power has to meet demand. There's different capacities on the lines, and there's limits on how much a generator can produce. Again, this is very, very simple. This is just to give you a sense of the general idea of the problem. Now, there's a lot of interesting use cases where there's bi-level optimization over optimal power flow. Where optimal power flow is the inner problem inside some planning tasks. So you could be deciding how to build new lines for expansion planning, where to put new generators, what kind of generators, what they should be, what mix you want of renewables and batteries and whatever, how carbon costs can be incorporated and can steer decision making, and having differentiability through the OPF problem lets you do this bi-level optimization in a very straightforward way. And GPU acceleration makes this work with very large networks, at the size of a nation. And there was nice work along these lines by Anthony Gutierrez and others at Stanford, where they built their own ADMM-based solver and differentiated through it for the bi-level problem. And they got really substantial speedups from that. But again, this was a major research project. This is a paper. But we believe with Moreau, this is just, this is an application. This is something that's very, very doable with just a few lines of code. Last example, portfolio optimization. So this general idea with portfolio optimization is I have some risk metric. This is covariance. Danny could tell us about many, many others, but this is one. And then I have some sense of how my expected returns. So this is covariance of returns. This is the expected returns. And I'm choosing how to allocate among different assets to trade off risk and return. And this is an example. And then I have many constraints that could be mandates of the funds, different regulatory constraints. These are quite important. So here I'm saying that my weights be non-negative or greater than 0. And this represents a long only. So if W were allowed to be negative, that would represent short positions. And these, for a serious hedge fund, these constraints can be quite complex and extremely important. And certainly the risk control is extremely important. Now, there are a lot of people now who have had the idea, well, let's just have an AI, decide what to trade. Let's go wild and have the AI run my portfolio. And this is certainly a fun idea. But there are maybe some concerns that one might have about what, am I going to wake up tomorrow and learn that the AI lost all my money? And certainly, if you're a real hedge fund, you couldn't do this. But if you encode the portfolio optimization as an end layer, you can still do learning. You can still do some kind of whatever learning framework you want, because this is differentiable. And you can still have the risk control that a serious hedge fund would have. And so you can sort of have your cake and eat it too in this situation. And I wanted to call out, there was a nice open source implementation we found when we were looking at the CVXPY layers users. But at that time, CVXPY layers was very slow. So this was not as exciting as it could be. But we've done a lot of experiments ourselves with Moreau, and this works very well. It's very straightforward. So this is another exciting application. So we're very excited to share the solver. This is the link. Yeah, but please talk to me afterwards if you're interested. As I said, we're just starting on Monday to give out access. And we're excited to see what people do with it. Thanks so much. Oh, wait.
Okay, sorry, give me 1 second to check the schedule. One thing I want to flag is, so, we're getting interior point method accuracy on the solver. And also, do you want to talk a little bit about kind of, if you're solving a bunch of similar problems one after the other, are there any benefits there?
Yes, exactly. So yes, the interior point approach is really critical. We did a lot of experience with many different methods, but for this to be really reliable, you want it to be interior point. And so yes, in terms of solving many similar problems, yeah, there's a lot of layers that we built into the system to take advantage of that setup. So doing the symbolic factorization in advance, which is a substantial part of the solve time for the particular libraries that we use in NVIDIA. But then we've been experimenting with other interesting features as well. Shane, just like a few days ago, added functionality where it'll experiment with sort of all the possible ways, all the different combinations of device and linear algebra backend that we have available. So like CPU, GPU, but then there's also a variety of different solvers, like linear algebra solvers that we have for each backend, and see what's best for your setting. So it's kind of like an auto tune. Yeah, and in general, we're with integration with CVXPY layers, you're caching the mapping from the CVXPY problem into the problem data as just a matrix. That's the benefits of the DPP, the discipline parameterized programming. So, and we're going to continue to develop this thread because performance is really critical to be useful in this. Like, you're embedding this in a bigger system that's constantly running, and so we want to make this as performant as possible. It's not just like I'm solving a problem now and then, right? Where okay, maybe it doesn't hurt too much, right? This is a hot loop that's constantly running, millions of times.